Thank you for inviting me to this very interesting workshop. So today I'm going to talk about the measurement-induced entanglement phase transition. So this is a relatively young research field. I'm going to explain how this becomes now a very rapidly evolving timely research topic. So this work is done with three groups of people. So the first one is based on the hybrid Clifford circuit. This is one type of circuit which allow us to do large-scale simulations for up to several hundred qubits. The second type of the model is hybrid automaton circuit. This is this type of circuit provides both a numerical technique to understand quantum dynamics, and also it's a nice tool to analytically understand the evolution of the dynamics and making connection with some classical particle dynamics. The third type of the system is SYK, is based on the SYK model. So this is we know this is an analytically solvable model in larger limit. We construct some non-unitary SYK circuit and understand the entanglement dynamics in this type of circuits. So in all these three types of circuits, there is a entanglement phase transition. So this is the outline of my talk. So before I discuss this measurement-induced entanglement phase transition, I will briefly review three types of the quantum dynamics. The first one is a closed quantum dynamics. The second one is an open quantum dynamics. The third one is a rapidly developing new field. This is called monitored quantum dynamics. I will focus on this type of the dynamics. So after I introduce these three types of the quantum dynamics, I will explain the measurement-induced entanglement phase transition in quantum automaton circuit. And then I will provide another physical picture based on the non-unitary SYK chain to understand this entanglement phase transition. So, so I will first briefly review the closed quantum system. So we know that for generic quantum system, the system is interacting and is chaotic. We expect that the wave function can summarize under its own dynamics. For instance, we start with the product state with qubits, a lot of qubits in the system, and then we involve the system with a global unitary evolution. We know that after some time evolution, the system will be highly entangled due to the interaction and due to the chaotic property of the system. So the endpoint of the dynamics is typically a featureless summarized state with a volume law entanglement entropy. This is called the quantum summarization of the eigenstate summarization hypothesis. So, and under the time evolution, after very long time evolution, we expect that there is a no-code summarization. This means the no-code, if we look at the subsystem over here, the density matrix actually takes the reduced density matrix for this subsystem takes the thermal form, and the expectation value for the local observables approaches thermal expectation value. The energy of the system is specified by is determined by the initial energy of the initial state. So this quantum summarization physics can be understood in terms of a quantum circuit model. So we could design unitary quantum circuits to understand the quantum evolution, because for a generic chaotic system, it's difficult to analytically solve these models. So that's one motivation for us to introduce unitary quantum circuit model to understand the entanglement dynamics, information scrambling, and night cone structure, also the quantum butterfly effect. So there has been a lot of work along this direction in the last decade. So in the unitary circuit, we are in this talk, we are interested in the circuit with local interactions. So we describe this, we consider circuit, let's say with a composed of two qubit gate over here. The gates are applied on the neighboring qubit. So after some time evolution, the system, the entanglement entropy for a subsystem will grow linearly in time and eventually saturate to a volume law scaling like this. So there has been a lot of development in this field, unitary quantum circuit, in some special cases, we could analytically understand these properties, like entanglement dynamics and information spreading and quantum butterfly effect. Okay. So, however, in reality, we know that all these systems are coupled with environment. For instance, Google has a quantum computer. We can apply quantum gates on the system, and this there are in 2019 they already have a quantum chip with 53 qubits. I think they now perhaps have the ability to build up a chip with maybe around 100 qubits. So in China, there's also some development in this field, roughly the same scale with 66 qubits. So in all these systems, we apply unitary gates. We want to understand the this closed quantum system dynamics, but in reality, is this system will is always coupled with the environment, in different ways. So besides unitary evolution, there has been a lot of development in the open quantum system to understand the dynamics, how does the dynamics coupled with environment, right? So this typically is we use this language, that is, we consider the evolution of the density matrix, and this is described by the quantum channel. So so in this case, the subsystem A will summarize due to the coupling with the system. Not only with the system, but also with the environment over here. So both the system and environment can be treated as heat baths for the subsystem over here. So and the entanglement entropy for the subsystem also has volume law scaling. Of course, in the system, in this case, and on a long-time evolution, the density matrix of the subsystem will summarize. So this is a closed quantum system and open quantum system. So one question we would ask is, what will happen if we have the ability to extract information from the environment? So this is called the monitored quantum dynamics. So if we can extract the information from the environment, so in this case, we will know some information about the system. We will know the information about the system, and the system may not summarize. So in this case, if we look at the subsystem A over here, entanglement entropy may not have volume scaling anymore. We will discuss this in detail soon. So a typical approach to understand this physics is through this quantum trajectory language. So we now is considering the pure quantum state evolution of this of the system. And this is the evolution will condition on the measurement outcome. So basically, instead of studying the density matrix in the open quantum system, we are considering the non-unitary evolution for the quantum trajectory of the system. Okay. Any questions so far? So I already introduced 3 types of the dynamics: closed quantum dynamics, open quantum dynamics, and monitored quantum dynamics. We will focus on this monitored quantum dynamics and see if there's an interesting physics in this. Okay, so a way to understand this monitored quantum dynamics is to construct introduce some quantum circuit model. So Toya model is something called a hybrid quantum circuit. So there are, in this case, different from the unitary case, we now have some measurement gate. So unitary part is still is still composed of 2 qubit gates. We consider circuit with local structure. So the unitary gates are these blocks, and are applied. They are applied on the neighboring qubits. So while the measurement gates we consider is local measurement gates applied on a single qubit like this. So in this circuit, there's both local unitary and projective local measurement. So we are interested in the quantum trajectory of the pure quantum state. We want to know what will happen for the quantum state over here after some time evolution. So notice in this circuit, there's a one tuning parameter that is a measurement rate. Measurement rate P here means the number of the measurements at each time step, the ratio between the number of the measurements and the number of the qubits over here. So the P is a tuning parameter, can be from, and there are 2 limits for this. One is P equal to 0, and 1 is equal to 1. So like so this question, like what will happen to this monitored quantum system was first like studied by these 3 groups. So at that time we are using like so we are using different quantum circuits. So in the first one like paper over here, so they were mostly focusing on the hard random circuit, while we were doing at that time is like we consider Clifford circuit, which allow us to do large scale simulation. So before I show some results. We can first consider 2 limits. These are 2 limits that's pretty easy to understand. The first limit is when p is equal to 0. So in this case, this corresponds to the unitary dynamics. We have discussed this before, that in this case, system will thermalize, entanglement entropy will saturate to the volume law. Another limit is p equal to 1 limit. So it means that we do measurement at every site over here, at each time step. So this after the measurement, for instance, we could consider local Z measurements. So the system will become a product state and there's no entanglement in the wave function. So the projective measurement, we know that tends to reduce the entanglement. So there's a competition between the unitary evolution and the projective measurement. So unitary evolution tends to increase the entanglement, while the projective measurement will like suppress entanglement. So one interesting phenomenon is this like entanglement phase transition. So in this case, for here we will consider, most of the time we'll consider like a one-dimensional system, meaning that we have a one-dimensional quantum chain and we apply unitary gates and local measurements on the local measurements on this quantum dynamics. So in the system, like as I said before, there are 2 limits. One is p equal to 0, another p is equal to 1. This case has volume law scaling. This case is a trivial product set. So one interesting question we could ask is there like a phase transition between them? It turns out that the answer is yes. In the system, in a generic system, like there is a phase transition. So and there's a PC here is like is some like a non-universal quantity. Like this is like model dependent. What is interesting here is that there's a volume law phase. There's a stable volume law phase, which can survive under the under the measurement when the measurement rate is weak. So another phase is this like quantum zero area law phase. When the measurement rate is large, the system cannot maintain entanglement, volume law entanglement anymore, and will become area law like disentangled state. So there is a transition between them, and like and in particular around this PC, like there's some interesting quantum like criticality, because this transition for generic case is a continuous phase transition. So different from the like conventional system, we know that in a conventional phase transition, like described by the Landau theory, that there is an order parameter. Order parameter is some physical observables. For instance, in Ising case, Ising model, the physical observable is a local magnetization. So magnetization is finite in the ordered phase, and as we increase the temperature here, there, and the magnetization will decrease and eventually become 0 at critical temperature, and it remains 0 at high temperature regime, which is like disordered phase. In our case, we could use a similar picture, but the like order parameter here is not some like physical observable, is the entanglement entropy itself. So if we look at the entanglement entropy density over here, like entanglement density is finite. It's finite at like when PC is small. This corresponds to some low temperature phase of the Ising model. As we increase the measurement rate, like the entanglement entropy density will decrease and eventually become 0 at PC, and remain 0 when P is larger than PC. So this is like a measurement induced entanglement phase transition. We are interested in this type of the phase transition because like when we identify the phase transition, we could analyze properties around this point, see if there's an interesting physics like around the quantum criticality. So one picture is like more interesting picture is this percolation picture based on this work. So what they found is they were considering is this hard random circuit. So like means that unitary gate here is a hard random gate, some like type of the unitary gate. In this case, they were able to map this like they were able to map this lattice to this problem to a bound percolation problem. So each dot here over here is this 2-qubit gate, and this like measurement here is like some broken bonds over here. So this maps to a bound percolation problem. The probability for this bond to be broken is P here, is a measurement rate. So in this case, like this becomes the geometrical problem, and the entanglement entropy, they were looking at S0. S0 is like a ring index, like equal to 0. It's a very special entanglement entropy. It only is counting the like bond dimension of the subsystem. So this quantity is like it becomes the geometrical quantity is a minimum path, like separating the lattice into 2 pieces. So this could be treated as a spatial direction, while this is like a time direction. So it is a 1 plus 1D system. One is from time direction, another one is coming from the spatial direction. Okay. So entanglement entropy, like when we compute the entanglement entropy for a subsystem at some time, it's basically we are introducing like 2 points over here. We are counting the we're looking for the minimum path separating the lattice into 2 pieces. So this is a very nice geometrical picture. It's introduced in this paper, and in this case, the entanglement transition maps to a like a percolation phase transition. We know the percolation in 2D case is a conformal field theory. It's a critical system, has some interesting but some special properties and different from the some rational CFT. So okay, this is a nice picture to understand this entanglement transition. So what we were doing at that time is like we construct a circuit which allow us to do large-scale simulation. So we consider this like a conifer circuit model. So in this conifer circuit, like we were able to simulate simulate system for like up to like thousands of the spins, qubits. So we could study the physics of this like we could study the physics of this hybrid circuit, and there is a transition in this. So we could we like compute the entanglement entropy in different geometries. For instance, we could consider this like type of the system that we have a qubits. We have system we have system coupled with environment. I will come back to this later. So this is called purification dynamics. It's introduced in this paper. We could identify like we could use this purification dynamics to identify the entanglement phase transition. So another type of circuit is like another type of the geometry is like we introduce some like qubits, not only in the spatial direction, but also in the time direction. So in this case, we can show that the system, like there is a criticality. In particular, the system enjoys conformal symmetry, similar to the like percolation picture I introduced before. However, what is different is like in this conifer case, the critical point is some unknown conformal field theory. We don't really understand the physical properties of this. So okay, so in summary, like I consider the two types of the hybrid circuit. One is a conifer, one is a hard random circuit. So we have this minimum cut picture. So this minimum cut picture only works for S0 or some large D limit. D is like the dimension of the local qubit space, and it's difficult to like generalize the picture to ring index like n larger or equal to 1. So we don't really know the physical property of this like of the like Von phase transition or second ring entropy, or the entanglement transition for the second ring entropy. Those are more interesting quantities like and so but we have no idea about the phase transition for them. So another type of the circuit is like conifer circuit. So this like allow us to do now numerical simulation for another system. We get a set of critical exponents, but we don't really know how to analytically understand this like underlying like a critical point. So this motivates us to like construct some models which allow us to do some analytical calculation, or at least to provide some physical intuition for this measurement induced phase transition. So in this talk, I will consider two types of the circuit. One is this like circuit is like a quantum automaton circuit. Another type of circuit is based on the SYK model. In those two types of system, like we could both do numerical simulation and we can do some analytical calculation for them. Questions for so far? Okay, if there's no question, I will first consider the first type of system, this quantum automaton circuit. So quantum automaton circuit is a very special circuit. So in this case, in this model, so the unitary gate is called the automaton gate, which actually is pretty simple. It maps so we first start with some computational basis. We choose the poly Z basis as a computational basis. So we could map one. So the unitary gate here maps one configuration, like one basis to another computational basis up to a phase. So it's like a permutations like of the computational basis. One example is this C0 gate. This 0, 0 maps to 0, 0, 0, 1 to 0, 1, 1, 0 to 1, 1, 1, 1 to 1, 0. So there's no, so it's just a like 1-to-1 mapping in this like case. No superposition. Another type of the gate is this CZ gate. It is like there's a phase over here for this 1-1 state. The rest of them remain the same. So so there are some, so in those gate, in those like automaton circuit, automaton gate, quantum gate, there's no superposition. So this gate like 0 maps to 0, 0 plus 1, 1, 1, 1 to 0, 0 minus 1, 1. This does not belong the although this is a unitary quantum gate, this does not belong to this automaton gate because there's a superposition under the dynamics in the computational basis. So we use this like automaton like gate to construct some unitary circuit. So this circuit has also been used to understand many interesting problems in the unitary circuit, like to understand conversion functions, like information spreading and entanglement dynamics. It's a very useful tool because this circuit like can provide some very efficient algorithm. So if we compute some physical observables that maps to some classical Monte Carlo, we can use some classical Monte Carlo sampling algorithm to compute this physical observable efficiently because the wave function is equal weight superposition of quantum state. So if we choose the initial state as equal weight superposition of quantum state, the wave function will remain to be an equal weight superposition of the quantum state. So it's a very nice like circuit which allow us to do large-scale simulation and also provide some nice intuitive picture to understand the entanglement dynamics. So in our case,
excuse me. May I ask a question
about
the I mean previous slide? Yeah. So what do you sample? I mean, as the examples of the gate pi, you mentioned about control node and CZ. But so you have various gates randomly?
Yes, unitary pi. Yeah. Yes, we
unitary.
Apply some.
Yes. Okay, equal weight superposition of various.
Right, I forgot to mention it over here. So we need, let's say we consider initial condition to be the wave function is equal weight superposition of the computational basis.
Yes.
And under the time evolution, because we are applying this unitary QA gate, so the gate will map like it's like a permutation group.
Yes.
Well, it's like a permutation. So the wave function will still be equal weight superposition, and all the information is encoded in the phase. The phase could be random.
Okay.
And the phase is very important. And I will show later that this can lead to different interesting quantum states. All the information is encoded in the phase. If once we fix the computational basis.
Okay, thank you.
Yeah. So, right. So the information is encoded over here in this phase physics. So this is important. Sorry, I forgot to mention it over here. So, and so it's not important, to understand the derivation here. I will explain the physics behind it. So we are interested in the entanglement entropy. In particular, we are interested in ring entropy. Let's, in our case, we could take n to be equal to 2 so that we look at the second ring entropy. So, and for the second ring entropy is equivalent to a swap, computing the some expectation value of the swap operator. So defined on the doubled geometry. So we need basically two quantum state, two copy of the quantum state. This is a standard trick when we compute the second ring entropy. And we apply a swap gate to like swap the subsystem over here, and we could show that analytically show that the purity of the subsystem is summation over the phases. The phase is coming from is a phase we discussed over here. And we sum map all these phases like of the between like bit stream pairs M1 and M2. So there are in total 4 to the power L bit streams. L is the number of the qubits over here. It's 4 because we are considering n equal to 2. Okay, so the secondary the purity can be computed in this way. So like let's consider some random unitary evolution. We expect that so let's use this formula. We expect that after long time evolution, all these phases are random. So and if we sum them up, the random phase will cancel. We should get 0, right? Yes, this is true for most of the states. And there are like some special cases if the A1 and A2 are equal, or B1 and B2 are equal. So on the time evolution, their phases will cancel and they don't contribute phase to the purity. So like so when let's consider a special case when LA is smaller than half of the system. So purity will like dominated by the configuration when the A1 is equal to A2, this spatial configuration. So we can show that the trace row A square is equal to like 2 to the minus LA, and leads to the maximum volume node scaling. So this is like a special case. We consider random unitary evolution that we can show that all these phases are random except one spatial configuration, that is A1 equal to A2. They don't contribute phase. So but they can contribute to the entropy, entanglement entropy. Based on this picture, we will consider like more complicated non-unitary dynamics. So let's consider now introduce measurement. So if we consider initial state is polarized in X state direction, so that is equal weight superposition in the Z basis. So on the unitary plus projective measurements, so we could consider 2 types of the projective measurements. One is a projective Z measurement. So if we consider Z measurement, this will permanently remove basis state. The number of the bases in the wave function, it will decrease with the time and eventually become 1. So when P is larger than 0, steady state is a single computational basis. There's no entanglement in it. There's no transition in it. So this is not what we want. Therefore, we could consider projective element X measurement. So there is an entanglement phase transition. However, it is not superposition of bases with equal weight. We were not able to understand them like this transition analytically. So we will like construct a very special measurement gate to allow us to understand the physics like analytically. So the gate is very simple. We first do a Z measurement, and then after doing the projective Z measurement, we will perform a rotation to the X or plus X or minus X direction. So we define this to be composite measurement. So every measurement is followed by a rotation. This is a Hartmann single qubit Hartmann rotation. We could let's consider one example. So let's say wave function is like superposition of these 2 states. So and this is like we do measurement on this side. This side could be like spin could be pointing up or like pointing down, right? We do the Z measurement on this side. So after doing Z measurement, it's either this one or this one. If we choose this one as a quantum trajectory, we get this wave function. So this qubit now is disentangled one from the system. And then we do a rotation at this qubit, single qubit rotation, rotate it back to plus superposition like a plus and a minus. So if the psi 1 is equal weight superposition over for the wave function, so entire wave function is an equal weight superposition for the like entire basis. So we use this gate like combined with this unitary gate, quantum automaton gate, we can construct a quantum circuit. We call this like a automaton circuit with composite measurement. So in this case, the wave function at any time is equal weight superposition of computational basis. Okay, And we are interested in the physics in this circuit. So like as I said before, if we want to compute the second range entropy, we need to consider the doubled like space, doubled like wave function state. So we have M1 and M2 over here. So, and each of them is bit string. So let's look at their difference. How do the difference could be considered as a particle, because it can be 0 or 1, two at every side, two possibilities. We could consider the evolution of this like corresponding classical bit string dynamics. So under these gates, under the unitary dynamics, so the difference actually will spread out in time. Like if the difference initially is localized, could spread over the entire system. Okay, and on the other hand, the composite measurement here, what the measurement will do is to like suppress the difference. So if we do measurement over here, they all become 0. Initially, if it's like there's one particle occupied, one particle meaning is like state is the difference is 1. They all become 0. So there's a competition between them, because unitary evolution, for instance, if it's C0 gate, like tends to spread out the difference, while the composite measurement will suppress the difference. So this could lead to a phase transition. It's called a classical phase transition here. And this classical phase transition belongs to the directed percolation universality class. We could first consider two limits. One is P is equal to 0. So the difference, a typical state is like, will be some state like this. And the difference, like if we consider Hamming distance or the number of the particles over here, it is extensive. If we consider density of it, it's finite. Okay, and in another limit, when P is equal to 1 limit, all the like sides are measured, all of the sides are measured and becomes 0. So there's no so the particle density is 0 over here. So, and the competition between them, unitary evolution and measurement, can lead to a phase transition. And this phase transition here belongs to the directed percolation universality class. And see, this is similar to what I introduced before for the like percolation, like lattice model. Now, but however, here is a different universality class. It's directed percolation. Okay. So this is one example of the directed percolation, that is called bond directed percolation. So there are different types of systems. They all belong to the same universality class, belong to the directed percolation universality class. It's very robust. So, and we could consider two cases. Initially, we start with one particle here and understand the like particle density evolution. Under the dynamics, bound directed percolation, let's consider. So around at a critical point, particle density will increase as a power law function and then eventually decrease again. So this like is a universal behavior. Another one is starting from the like all the sides are occupied by particle. We want to know how does it evolve with the time. It will decrease, eventually decrease to 0. It decay also as a power law function. So these are like some like properties of the directed percolation. So different from percolation, directed percolation is anisotropic in spatial and temporal direction. So dynamic exponent Z is not equal to 1. It's close to 1.5. So it's a critical system, but it's not conformal because the dynamic exponent Z is not equal to 1 here. So let's come back to this quantum case and then understand. We now know that this quantum phase transition should also belong to this like directed percolation universality class. The question we are going to ask is, what's the corresponding quantity for the entanglement entropy in terms of this classical like particle dynamics, right? So this is actually a very interesting question. I directly tell you the answer, like, and skip some derivations. So based on the picture we introduced before, that's we are counting remember that when we compute the purity, it's summation over like random phases. Most of the phases will cancel. We are looking for the terms which do not contribute to a phase, which will instead contribute to this purity. Okay, so and if we compute entanglement entropy for a subsystem A over here, if we consider bipartite entanglement entropy, let's consider simplest case. There's a boundary between A and B. So in A, So there we could introduce two types of particle. One is X particle, another is like Y particles. So let's consider the evolution of the particles under under this time of evolution, dynamics of the particles. We know that particle can spread or be killed, got killed due to the measurement. So it turned out that the purity is equal to the fraction of the number of the configurations in which X particle and Y particle do not encounter up to the time t. This is called the first passage problem in in the directed percolation problems. And in the voluminal case, this number decrease expansion in time, which leads to the linear growth of entanglement and also responsible for the voluminal scaling of the entanglement. At a critical point, this fraction, the fraction here, the number of the configurations which do not, in which X and Y do not encounter up to time t, will decrease as a polynomial function. And this leads to the logarithmic growth of the entanglement in the time direction, and eventually leads to a steady state, which is also logarithmic in the subsystem size. And the coefficient in front of them is for the time direction, it is equal to alpha, while in the spatial direction is alpha times z. Z is a dynamic exponent. Alpha is also a universal number, and it's called the local persistent coefficient. So therefore, we successfully map the entanglement phase transition to a stochastic classical particle dynamics. In particular, we can show that entanglement entropy, this quantity, second range entropy quantity, maps to some first passage problems in this classical particle dynamics. And the coefficient alpha here is a universal coefficient in the classical directed percolation universality class. So therefore we could check this numerically. We do construct a hybrid automaton circuit. In particular, we use this Clifford gate to construct a subset of the automaton gates. So we can show that we can easily do simulation for a few hundred qubits. So we first identify the critical point. Critical point is around the p equal to 0.138 in this circuit. And then we could show that the critical point, there's some logarithmic growth in time direction, and also the logarithmic growth as a function of the subsystem size. So we compare them numerically. Look at the coefficient. We get this critical exponent as a dynamic exponent consistent with the directed percolation universality class. We could also further perform data collapse around the critical point. We obtain some critical exponents for the coordination length in the system. It's also consistent with the directed percolation universality class. So we can further use this suspicion to understand other problems geometrical problems like quantum purification dynamics, which is in this case, we could also show that the entanglement, the entropy for subsystem A maps to some classical quantity in the particle dynamics, and it's a similar problem. We could further do some numerical calculation and show that this is consistent with directed percolation. So this is a nice physical picture for this model provides a nice physical picture to understand this measurement induced entanglement phase transition by mapping this to a classical particle model. So furthermore, this nice picture also provides builds up the connection between quantum error correction code and a classical linear code. I don't have much time to discuss them in detail, but I want to mention that this measurement induced phase transition, the voluminal phase, could be treated as an error correction code. That is why another reason why it is stable under the infrequent measurement. So in the automaton circuit, we can show that the corresponding classical dynamics is indeed a classical linear code. So this model has an interesting connection, builds up interesting connection with a quantum error correction code and a classical linear code. And in particular, the code distance for this model diverges in the in the thermodynamic limit. It's also indicate that why the system is stable under the infrequent measurement. So let's run to the second topic. That is like the measurement induced phase transition in non-unitary circuit. So I'm running out of time, so I will briefly, just explain the most important physics in this model. Okay, I will skip some technical detail. So basically, what we are doing is like we use SYK model to construct some analytical solvable non-unitary circuit. So we use one type of the SYK model called the Brownian SYK model. So Brownian means like SYK model is like is a four body interaction terms, and is composed of Majorana fermion, and the coefficient u here is a random variable. And for the Brownian SYK, u is not only a random variable, it changes it's a random walk in the time direction. So meaning that so this is this random, and it's there's no correlation between different times. This is called the Brownian SYK model. So this model is also analytical solvable in the larger limit. We get the set point solution for this model. And what we are doing, what we are considering is we use SYK model this SYK is a non-local system, has non-local interaction. We use SYK model to construct some one-dimensional chain. So in this one-dimensional chain, each dot here is a SYK. It has a number of the Majorana fermion, and we will push n to infinity. So in the larger limit, we can analytically solve this model. So there's on-site interaction between the interaction within each dot, and there's an interaction between neighbors. So all of them are four body interaction. Okay. So this is a unitary part. So we consider two chains. The reason we consider two chains is for computational convenience, as we will show later. So in this case, we have two chains. Each of them is Hamiltonian is the same, and all of the interactions here is Brownian. The coefficient is Brownian, and so this is for the unitary dynamics. Now let's introduce the measurement part. So measurement is we introduce measurement between these measurement is on this defined over here is a projection, is parity projection. So it's defined within these two chains. And and on the time evolution, this will effectively lead to an imaginary term in the dynamics. Okay, like this. So the mu here could be treated as a measurement rate. So what we expected, what is expected from this model, right? So we could consider is the first, the unitary dynamics will scramble the information, right? A system will become highly entangled in the spatial direction, and the measurement here will disentangle different sides, but entangle the left and the right chains. So it eventually will become we could treat it as a product state in the spatial direction, right? And there's a competition between the U and the measurement, which can lead to a measurement induced entanglement phase transition. We're going to characterize this phase transition by the quasi entropy. So it's slightly different from the entanglement entropy, because for the entanglement entropy in the random system, we should take the average over the entire log of this quantity. Here, for the computational convenience, we are taking expectation value over here inside of the log. So I don't want to go to the technical detail, but this do make the calculation much easier to handle. So the expected, we are averaging over the Brownian variables, and the continuous monitoring outcomes. So we will consider n equal to 2 cases. So in this case, there will be 4 copies of the state, because we are considering 2 density matrix, and there are 2 forward, 2 backward. These are some technical detail. You don't need to worry about this. Using the knowledge that the SYK model can be analytical solved. So we consider this one-dimensional chain system, and we write down the Nargen set point solution for this one. So this is a Nargen set point solution. This part is unitary part. This part is a measurement part. Okay, and and then we could consider the compute the Nargen solution for this model. Okay, And what we are going to do is after we obtain this larger solution, we will consider the fluctuations around this around this saddle point solution. We write down the effective action for this theory. So, and the effective action turned out to be pretty simple and beautiful. It's just a Ginsburg-Landau theory. And we know that there is a phase transition in this model, right? By tuning the R over here. R is a parameter like this. It's depending on the coefficient of the R, right? The value of the R. If it's positive, it's in some disordered phase. When R is negative, there could be the ordered phase, right? That's for the Ginsburg-Landau theory. So here therefore we map the entanglement phase transition to a conventional phase transition in the enlarged replica space. It's replica space because we are computing the entanglement entropy. We need to introduce this replica space. Here the replica space n is equal to 2 here. So we can compute the phase diagram. So this one is there is an emergent Z4 symmetry in this Ginsburg-Landau theory in the replica space. So this emergent Z4 symmetry is interesting. We could and in the when I is negative, is with the system spontaneously breaks the symmetry, correspond to the voluminal entangled phase. When I is when I is positive, this restores the symmetry in the this is in the areal entangled phase. I could be it's like this. The ratio between, so if we define draw the phase diagram as a function mu divided by j, this part is symmetry breaking, while this part is a symmetric phase. There's a spatial point when there's no interaction, that is u equal to 0 case. So this is could be correspond to some at this point the symmetry is enlarged, becomes a continuous symmetry, and then there's a Goldstone phase, a Goldstone mode over there. So this is a critical phase. I will not discuss this one. This corresponds to some interesting free fermion, non-unitary free fermion problems. It's also interesting, but I will not discuss it over here. So this is a spatial line when u is equal to 0. When u is non-zero, there's a voluminal to areal transition. So when u over j, the ratio is smaller than 1/2, it's a second order, while uj larger than 1/2. It shows that in this model, it's a first order transition. Anyway, there is a voluminal to the areal phase transition. In this case, we could an entanglement entropy correspond to insert some boundary changing operators on the boundary. Basically, compute the energy change of the after inserting some twisted operators on the boundary. So we could also further for this for this case, for this model, we could also numerically compute it because we know how to entanglement entropy is the effective action is written in terms of this green function. So we could compute the entanglement entropy numerically by solving the saddle point solutions. So this is and we numerically checked it. We compute the entanglement entropy and the mutual information for two disjointed regions. We can show that it's consistent with what with the phase diagram we drew before. Okay, so the take-home message for this for this SYK model is this we basically treat, let's summarize over here. So we treat this trace row n. So for here we take n equal to 2 here. It's a purity. We consider this compute this in the replicated space, and there we can show that the entanglement phase transition maps to a enlarged there's an emergent enlarged symmetry in this case, and the entanglement transition maps to the symmetry breaking phase transition in this enlarged emergent phase space that is described by the Ginsburg-Landau theory, and the entanglement entropy correspond to some free energy change of the of the boundary domain walls. Free energy change by introducing some twisted operators, which can effectively introduce some domain wall configuration in the system. Basically, is computing the domain wall in the free energy of the domain walls. So in the voluminal phase, the domain wall energy is extensive, and this sigma here could be considered as some surface tension. As we sigma approach, as we increase the measurement rate, sigma will decrease, eventually become 0 at a critical point. So this picture is not only appears in this SYK technique, it also appears in other works. It first like people have been using this to understand the random tensor network holographic duality in the random tensor network, where they map this to some like Ising models like over there. And also like over here, in this paper, in the second one, is they were studying some entanglement phase transition in the random tensor network. So it's similar picture. They map to this like to some like to some free energy, to some like to a statistical mechanics model. There is a phase transition, order to disorder phase transition, and the entanglement maps to the domain wall free energy problem. And this work also, this like idea also appear in the hard random unitary dynamics, where this is like entanglement entropy also maps to some domain wall picture. And this picture is also used in the like hybrid hard random circuit, which involves both unitary and the projective measurement gates. Okay, so in this picture involves in all these like systems, like showing that entanglement phase transition can be mapped to some like symmetry breaking phase transition in the enlarged replica space. So, okay, in summary, I have provided two pictures to understand the entanglement phase transition. The first one is based on this quantum automaton circuit. So this one maps the entanglement phase transition, the entanglement phase transition to a like classical phase transition, which belongs to the directed percolation universality class. And the entanglement entropy, the quantity secondary entropy, is mapped to the first passenger problem in the classical stochastic dynamics. So this provides provides one approach to understand the physics in the measurement induced phase transition. So this could be considered as a small n limit. And another limit is this large n limit. This is like a mean field theory in some sense. That is, we show that this entanglement phase transition maps to the symmetry breaking phase transition in the replica space. And there's a entanglement domain wall picture. So this like measurement induced phase transition has got a lot of attention these days. And it turned out that not only the phase transition, but this like monitoring quantum dynamics provides an efficient tool to prepare some interesting quantum states, which cannot be, it's difficult to prepare in other more conventional approach, like unitary circuits or the ground state of some like quantum phases of the quantum interacting quantum systems. So this has become, this monitored quantum dynamics has become a relatively active research field these days. We have a lot of like better understanding of this dynamics, use this to prepare like different quantum phases. Another application is on the quantum information. So, and on the, as I mentioned before, that this model can be treated as a quantum error correction code, the voluminous phases. Besides this quantum error correction, this can also be used to understand some computational complexity problems in the quantum information theory. And besides the quantum information, this perhaps can also have applications on high energy physics. For this part, I'm not very familiar with this, but I believe there are many experts who are working on this field for a very long time. So this like monitored quantum dynamics has become, I believe that there could be many interesting problems if we like further explore in these directions, two directions. So that's the end of my talk. So thank you for listening.
Okay. Thank you very much for your stimulating talk. Now we have about 6 minutes for questions and comments. So please raise your hand or unmute yourself. Okay, may I ask one question? So about preparing a state using monitored dynamics, if you use some post-selection like protocol, then as the system size becomes larger, the probability for getting the desired state, does it become exponentially small?
Yeah, this is a very good question. Actually, I did not mention it in the talk, but it's a technical problem in this, monitor the dynamics, the post-selection problem. Yes, if you want to get the same state, you need to, as we increase the system size, you need to, get like it will require exponential resources because it's getting more and more difficult to get the same state. For instance, if you want to experimentally detect this phase transition, like we need to, if you want to like measure this entanglement transition like in a real quantum. Let's say I give you a quantum computer and we can run this circuit, right? And if we want to get this observe this phase transition, entanglement phase transition, we need to get the same states multiple times, because once you we know the way to observe to measure this entanglement entropy is to we need to prepare the state multiple times and do the tomography for the subsystem. We basically reconstruct the density matrix for the subsystem, and this requires post-selection. And this problem is an open question in this field. There's no efficient way to do this unless the circuit is very special. It's like some special cases, so we can do the avoid this post-selection issue. And this is an open question in this field, because all this physics, most of the physics, interesting physics, requires post-selection, and post-selection requires exponential resource. In particular, even we have a quantum computer, it's still very difficult to do post-selection.
Okay, thank you. So Tokiro, please.
Thank you for the interesting talk. And actually, I have two questions. The first question is about the first part, and so you mentioned some directed percolation, and so I want to ask whether it is described by conformal field theory, and in that case, is it already known?
Yes, I mentioned it. Some over here. I think. Let me. Yeah. So this actually, directed percolation is a critical system. Let's consider 1 + 1D directed percolation. The problem is this model is anisotropic in spatial and temporal direction. It's not it's anisotropic. It's not isotropic. Percolation is a CFT. It's some a very special some CFT we understand, but it's not it's a non-unitary CFT. Directed percolation seems to be more complicated than that. It's not that complicated. It's not a CFT first, because anisotropic in spatial and temporal direction. So dynamic exponent Z is it's not equal to 1 here. So this means imagine we have some using some cartoon picture that we can create some canisters in this bound directed percolation, meaning that at a critical point, meaning that those canisters, they are not isotropic in the spatial and temporal direction. In the 2D percolation, or 2D percolation, just these canisters are isotropic, and that's why they could have conformal symmetry. But over here, it's anisotropic. There's no conformal symmetry in this case, although it's critical. So
I see.
Still critical. This is still critical. Still an interesting critical system.
I see. But since the dynamic exponent is non-trivial, so I see. And another question is, in the SYK side, you consider the Brownian SYK, but so is it difficult to consider the ordinary SYK?
Yes, good question. So we could consider just the ordinary SYK. So that the coefficient here, they are not time dependent. So for this model, actually, is so we could do just consider this standard version, and there is a transition. First, I can tell you, but the physical picture is more complicated. So that's why we use this Brownian version. In the Brownian version, we can easily get this this effective action. But for the standard version, it's more complicated. In some special cases, we can also get a nice picture. Since we are the one motivation of considering this SYK is to understand the dynamics in the random circuits. Those random means both random in spatial and random in time. So it's natural to use this Brownian version of the SYK. In the standard SYK, we do have phase transition, but it's more complicated in many cases.
I see.
Also, technically, it's more challenging, I can tell you.
Technically, it will be difficult. I see. Yeah, thank you very much.
Okay, thank you. And let's thank Xiao again for his nice talk.